Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 29, 2026, just about 4 days ago. It introduces a new method called V-Pretraining that improves reasoning performance by up to 18% on benchmarks like GSM-8K, remarkably using only 12% of the training examples as feedback. The paper is titled Value-Based Pre-Training with Downstream Feedback. And as we'll see later, the results for both language and computer vision models are quite striking. Figure 1 illustrates the overall framework. On the right, we have the standard foundation model, or learner theta, which normally trains on a fixed proxy objective like next token prediction. In the middle, the pre-training task feeds data, such as masked text or augmented images, to that learner. The big change happens in the blue box on the left, where a component called the task designer phi comes into play. This designer uses a small set of verifiable downstream tasks to reshape the pre-training data, effectively steering the learner toward more valuable updates without ever training directly on the downstream labels. Well, Figure 2 demonstrates the practical impact of this steering, particularly regarding efficiency and control. On the left, the sample efficiency chart tracks reasoning performance against training tokens. The value-based approach in red climbs faster and higher than the baseline in blue, meaning it learns more effectively from the same amount of data. Then, on the right, the trade-off between tasks plot shows how the method handles competing goals, like segmentation versus depth estimation. The blue line forms a Pareto frontier, proving the task designer can navigate the trade-offs between different capabilities by adjusting feedback. So while the previous charts visualize the gains, Table 1 lists the exact performance improvements across both language and vision. In the language section, looking at the GSM-8K benchmark, V-Pretraining consistently beats the baseline. For instance, the 0.5 billion parameter model jumps from roughly 19% accuracy to nearly 23%. Moving to the vision results, the method improves metrics for depth estimation on NYUV2 and segmentation on ADE20K, which shows that steering pre-training benefits dense perception tasks without sacrificing general ImageNet accuracy. Alright, Figure 3 investigates two key scaling questions. On the left, the scaling feedback coverage chart shows how performance improves as we add more feedback data. Interestingly, the curve flattens out after about 2,000 examples, which implies that a relatively small set of verified tasks is enough to steer the model effectively. Then, looking at the right panel, we see the pass at K results. Here, the red bars representing V pre-training consistently stay above the blue baseline bars across all model sizes, showing that the method's advantages persist even when we allow the model multiple attempts to solve a problem. So Table 2 expands the scope to see how this method affects tasks that were never used for feedback. This is crucial to ensure that steering the model towards specific goals does not degrade its general abilities. In the language section, performance on Omega, a math benchmark, generally improves or holds steady, while general knowledge on MMLU remains comparable to the baseline. Then, in the vision section at the bottom, the results are even more positive. On image retrieval benchmarks like Oxford 5K and Paris 6K, V-Pretraining consistently boosts mean average precision. Well, having checked generalization, Table 4 now validates the source of these gains by ablating the feedback signal itself on the QN 1.54b model. The first column, value feedback, hits the top score of roughly 59%. In contrast, random feedback and uniform smoothing lag behind at about 54%, which confirms that the model really needs the true gradient direction, not just regularization. It also edges out self-distillation, showing that downstream guidance is more effective than the model teaching itself. Alright, since we've seen the performance benefits, Table 3 breaks down the computational cost of running this method on an H100 GPU. Looking at the value-based row, the throughput in tokens per second drops by about 16% relative to the baseline, and the time per step increases by roughly 19%. However, the peak memory usage grows by only 4%, which is quite manageable. Interestingly, the last column reveals that the specific value update calculation takes just over 2% of the total GPU time, implying the method is fairly efficient. Wrapping up, two takeaways stand out. First, a tiny amount of verified feedback can successfully steer massive foundation models during pre-training, boosting specific skills like reasoning without harming general knowledge. Second, this value-based approach works across both language and vision, offering a scalable way to shape model capabilities early on. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.